Okay, so far we have talked about the tensors, the scalars and the vectors, which are essentially zero order tensor and first order tensor. And also we have talked about the second order tensor, that is stress tensor. We have talked in detail. Uh, Today we are going to talk about the rotation of axis and how it affects your vector tensors. Let's suppose I have a coordinate system, and we told that we will start assuming we will start giving notation as 1, 2 and 3 as my coordinate system, and 1 dash, 2 dash, 3 dash as my rotated coordinates. Okay, and I will denote my vector as x down bar 1 down bar, and second order tensor as the tensor with double bars down it. The components which I will take in this particular course is x1, x2, x3, and unit vector or the basis vector, where generally we take as ijk, will take here as a1, a2 and a3. Okay, why we did not keep this ijk, because these things are reserved for tensor notations, which we'll see in a while. So x is my a vector that is denoted as x1i, x2j, x3k can now be written as x down bar as x1 a1, x2 a2 and x3 a3. Okay, and this x bar is equal to x1 a1 plus x2 a2 plus x3 a3 can also be written in terms of summation in the index form, index notation. You can write in index notation as summation of xi ai, where I goes from 1 to 3. We can also write in this particular form in compact manner, right? One more thing I want to put things in notice here, that this can again be written in terms of in matrix form. In matrix form we can write this simply as the column vector, and different components I can write as x1, x2 and x3. The moment I write in form of vectors, I mean in column wise, I do not need this a subscript, because it is obvious that the first component corresponds to a1, a2 and a3. Along this unit basis vectors, these components are aligned. Okay, so this is another form to write. Similarly, we will also follow this notation as x transpose as x1, x2 and x3. Okay, now let us do some rotation, and let's see what happens to a particular vector that is aligned in a space. Let's suppose this is my particular vector that I am talking about. This is my x bar, and this x bar is being written in terms of x1 times a1, x2 times a2, and x3 times a3. And why this is important, I mean, slightly you guys think that I'm going into too much of rigorous things, but have my words, these things are will be useful while we were discussing our overall governing equations in the form of index notation or tensor notation. It will be very useful. Okay, it will be widely used. That is why I am doing this. Now what should I do? I'm going to rotate. I'm going to rotate this axis. So this axis will be rotated somewhere here. This axis correspondingly will be rotated in this fashion. This is my 1 dash, 2 dash, and 3 dash. This was my 1, 2, and 3. And this was my O origin. Okay. We'll see in a minute or so that you're rotated. So this was your x. X was written something like this. Okay. So you're rotated rotated vector x bar dash. I'll denote this thing in dash, written as x summation of xi cij, where I is equal to 1 to 3. In the expanded form, I can write x1. I'll not going to do the detailed calculation for 3-dimensional case. I'll not do that because it will be cumbersome. I'll take up a 2D case, and I'll show that how these rotated vectors are written in terms of uh, previously denoted vectors and some transformation. So this is your previous this the original vector, and this c subscript is your transformation coefficient Cij. So this can again be written in terms of x dash j, can be written as, or more precisely it is written in form of xj if I am not writing in the vector form. So x dash j, this can also be written as x dash j rather than vector, because j will go from 1 to 3, so it is a vector. Since it is essentially a vector, xj can be written as x1 c1j, x2 c2j, and x3 c3j. Okay, notice that here there are 2-3 things. Notice that the index 1 1 or here I are repeated, and this j index is free index, and this is your repeated index. What does this mean? Repeated index means it is being repeated. Okay, in the same course of notifying the tensor, it has been repeated twice. So it is called a repeated index. So I is a repeated index here, and we'll see the significance of repeated index in a while. Just to make you familiarize with the notations, this j is called free index, and j is also over here. So free index can be written freely. Okay. and repeated index are written by conjunction in twice manner. So here you can see you have these are repeated index, and this is your free index j. Okay, so in turn I can write three components, so these are my original components x1, x2, x3. Now I can tell that these are my rotated components x1, x2 and x3. Dashes are, so x1, what should I write x1 dash? So here x1 dash I can write as x1 c11, right, x2 c21, x3 c31. Similarly, x2 dash can be written as x2 c12, sorry, x1 c12, x2 c22, x3 c32, and similarly x3 dash can also be written. Okay, now so far I have not talked about what is C. C is essentially Cij is essentially my cosine, cos of angle between original or old subscript with new one. So this is my old subscript and this is my new rotated subscript. So we'll see how things worked out in 2D. So since you are not able to capture this, I am sure that you are not able to capture this. Once I start doing things with 2D, you will be able to capture how I've done things in two-dimensional form. So to do that, let me draw a two-dimensional coordinate system in this fashion. This is my 1, this is 2, this is 0 origin, and you have a vector x. You have x vector at position p. You have x vector, or to be precisely x bar. Okay, now I want to rotate this thing by some angle alpha 1 1. Okay, so now this two axis will also be rotated. So this is my 1 dash, this is my 2 dash. Okay, so this is my alpha 1 1. Okay, let me draw things in this manner. Okay, let's not worry about alphas right now. Okay, now my idea is to write my x1 dash and x2 dash, find x1 dash and x2 dash in terms of x1 and x2 and some coefficients if at all are there. Okay, can I write? So x is nothing but x here is x1 a1 x2 a2. Now I want to write things in it means x1 dash and x2 dash means now my reference viewing picture is in 1 2 dash reference frame, and now I want to look what is this vector that looks when you see from 1 dash 2 dash. That is my aim, right? So this is my aim. Now let's, so in order to do that, what should I do? I want the perpendicular length. What is this length? I need to devise this length, and what is this length on this particular axis. So as long as you find this one and this one, sorry, not this one, this one, you will find basically this component. Okay, let me draw one more thing. This thing will give you, these two things will give you the components of x1 and x2, isn't it, in your usual coordinate, right? इस x का component x1 and x2 मिलेगा मुझे 1 and 2 में, इसका 1 dash and 2 dash में जो component होगा वो मेरा क्या होगा? This one is x2 dash and this length is x1 dash, isn't it? And this is what I wanted. I want a relation between x1 dash x2 dash in terms of x1 x2. Okay, so in order to do that we need some angles. Okay, so let's one by one. Let's deduce x1 dash. So this length, right? This length. So this length is nothing but this particular length from here to here. So let's suppose I should rename some points, and I should recall some points. So this is your let's suppose A. Okay, this is your D, and I will make a perpendicular line over here, and I'll call this as C, and I'll make a again perpendicular line over here. I call this as B. Okay, so this angle is some angle. Let's call this angle as alpha 1 1. So what is my notation? Alpha 1 1 means this is my old one, this is my new axis. So I'm going from 1 to 1 dash or 1 to 1. Okay, if I want to take angle from 1 to 2, so 1, this 1 to 2 will be angle alpha 1 2. Similarly, and this would be my notation, or more precisely alpha 1 1 dash. Okay, okay, so can I write x1, this x1 whole length is basically my OD. OD is my whole length. This particular length is my OD, is the total length that I am telling x1 dash, and I want to write in terms of x1 and x2, right, lengths. So OD is nothing but OC plus CD, right? OC plus CD. So this length plus this length. Okay, now CD is again equal to AB. These lengths are equal. So I can again write OC plus AB. Okay, you just have to be patient. Once this is clear, I mean everything will be step by step, it will be clear. Okay, so what is OC? So OC is what? This length is x1. x1 cos alpha 1 1. Can I write OC as x1 cos alpha 1 1 dash? I can write, or dash sign I will remove for the simplicity. Cosine of x1 is OC. Similarly, this angle and this angle would be same. Okay, how? Can somebody tell me? This angle and this angle will be same. This is alpha 1 1. This is also alpha 1 1. Let me show you here. So let's suppose this is my alpha, and there is some other line that is perpendicular to this and perpendicular to this. There are two lines. So this is perpendicular here, this is perpendicular here. I want to revise that this alpha is equal to this alpha. How? So this alpha is alpha here, 90 here. This is 90 minus alpha, right? Then total will be 190. Since this is 90 minus alpha, this is 90 minus alpha. So this will be, and this is 90. So this is again alpha. Okay. So this is how you write this alpha 1 1 as the same alpha 1 1. Okay. Now, what is this length? CD length. CD length is equal to AB, and AB is equal to what? AB is equal to x1 times. So this length is x1. So this length is x1, straight length in terms of x1. So x1 of sine alpha 1 1 is my AB length, sine angle, right? Because this is perpendicular.
सर x2 नहीं आएगा सर वहाँ पे?
कहाँ पे? हाँ, sorry, this is
AB
x2. हाँ, x2 आएगा, right. This is x2. Thank you. Who is this? Who is this?
सर प्रभात.
Thank you, Prabhat. You are right. So ये x2 आएगा. Actually, this is x2. You are listening it seems. Because this length is x1 and this one is x2. You're right. Now, let's plug in it here. So I can write x1 dash is equal to x1 cos of alpha 1 1 plus x2 sine of alpha 1 1. Okay, now let's do one more thing, that is alpha 2 1. So this angle is let's suppose this angle is alpha 2 1. Alpha 2 1 means from 2, oh, it has some convention, alpha 2 to 1, it goes alpha 2 to 1, and this angle is nothing but 90 minus alpha 1 1. Okay, this is evident here. Now I can make a manipulation over here. X1 cos of alpha 1 1 plus x2 sine of alpha 1 1. I can write sine of 90 minus alpha 2 1, this angle. Okay, so sine 90 minus alpha, sine 90 minus something, sine 90 minus theta is cos theta, right?
Cos.
Right. So cos alpha 1 1 plus x2 cos of alpha 2 1, I can write. So we have achieved one relation, and this relation is very important. And similarly, if we go let me put a one slide, blank slide. Let me go to the quick manipulation over here, or should I not do that? If I do the similar thing for x2 dash also, I'll find similar. If you do the similar algebra, you will come up with this particular expression: x2 cos of alpha, where alpha 2 is this angle going from 2 to 2, and plus x1 cos alpha 1 2. Okay, now these two relations are important. Why? Now I can write my new coordinate, new vector, I mean rotated vector coordinates in rotated frame. Rather, let me put it in this way. Now I am ready to write my rotated vectors in some particular fashion. Can I write that? Yes, I can write that, right? So more precisely, let me write it again here. Let me write it again over here. So x1 dash, I have written x1 cos alpha 1 1 plus x2 cos alpha 2 1. Okay, I can now, so every time I don't want to write cos every time. Okay, so I'll put a small notation. I'll replace this cos as c. Whenever I see cos coefficient is there, I'll write c. Okay, and whenever I see sine coefficient, I can replace it with s, but generally we will not need it here because c will be sufficient, because everything I can convert into cos. And then I can write x1 dash as x1 c11 plus x2 c21, right? Similarly, x2 dash was written as x1 c12 plus x2 c22, right? Now you can see a symmetry. So whenever it was 1 over here, I am writing these ones over here. Whenever I am writing 2 over here, I am writing 2 over here. Okay, but notice here, this one, this 2 and this 2 are actually going from 1 to 2 and it is summing. This one, this 2 and this 2 are going from 1 to 2 and it is summing. So essentially this red line, this is very important. This red line is actually a free index. Red circle is a free index, and this blue circle is my repeated index. Okay, and now it is conveniently written as follows. I will write my free index as any index. Let me call it j, xj. Okay, xj means if I am writing j is equal to 1, if j is equal to 1, then follow this particular equation. When I am writing j is equal to 2, follow this equation. Okay, so when j is equal to 1, so it in general it can be written as x dash j x I c I j, and that's it, or summation over I is equal to 1 to 3. This is the way you should write, and once you write this, you are done with both the equations. How? When you put j is equal to 1, let's see, let's put j is equal to 1 over here. Let's say j is equal to 1, so x1 dash is equal to summation over x1 c1 1. So summation sign है, so I can do x2 c2 1, and this is similar equation what we have written here. Right? Now let's put j is equal to 2 here. What is j is equal to 2? X dash j x dash 2. तो जहां पे j j वहां पे 2 रख दीजिए simply. So this is x I c I 2, and I कहां से कहां तक जाना है? 1 to 3 या 1 to सॉरी 3 नहीं जा रहे हैं क्योंकि ये 2D केस है, तो 2 तक जाएंगे. So now I can go 1 x1 c12 plus x2 c2 2, which is similar to this equation. So no need to write explicitly all those bigger equations, just I will follow this particular notation. Right, whenever I rotate my coordinate, I will just tell that the components, the rotated components, can be written in terms of xi ci j. Moreover, one more thing I wanted to tell you guys, that the summation sign can be dropped. Why? So when Einstein was doing some manipulation in its physics, when devising the relativity theory, he was undergoing lots of ij, k's, and all sorts of notations, and he doesn't want to write summation sign all the time. So what he told, that whenever you see repeated index, just drop the summation sign. So essentially xj dash, rotated component, is nothing but I is equal to 1 to n, or some dimension x1 c1 j, or sorry ci. Okay, so when this is dropped, this is equivalent, this statement is equivalent to this expression xj dash is equal to xi cij. There is nothing wrong to say this equation is equal to this equation. This is essentially the same equation. We just dropped this summation sign, and this dropped summation sign is often called as Einstein summation notation. Einstein summation notation. And you will also don't want to write every time summation over here. Once I will see that there is a repeated index, I will see that there must be a summation sign over here which is hidden. That's it. I will not explicitly write things there. Okay, and this is called Einstein notation as well. Okay. And this is my free index, and this I is my free index is j, and repeated index is I over here. Why this is free index? This j is a free index. I can equivalently write xk dash is equal to xi ci k. There is nothing wrong to write k, because k again, where j I was taking from 1, j is equal to 2, another equation. K also I can write similar thing, k is equal to 1, k is equal to 2. I can write several equations, right? So these two things are essentially the same. One more manipulation I can do is x. I can also write xi dash is equal to x. Now I cannot write I here because I already taken, so I can put this thing as j, cj, and then this I would be coming over here. Now this would be the equivalent statements. All these things are equivalent, nothing wrong in it. All things means the very same equation. You can also write xp dash is equal to x pq cq cqp. Okay, unless until you follow the same trend, you can take any index you want. There is nothing wrong in it. Okay, and this is how we are widely using our index notation in this whole particular whole course. Every time I'll write in terms of I, j, k, and everything. Okay, so any doubt so far? Because this is important to know, and I want you guys to currently I'm going slightly slow, but once we understand, once we are accustomed to these sort of notations, then we will go very quickly and we will switch to the proper fluid mechanics problems and governing equations. Okay, that is what my understanding is. Okay, one more thing, since I have not much more time we have left, so let's do one more thing, that is a matrix multiplication. So matrix multiplications are generally written in terms of, let's suppose I have a times b, this and this is a matrix. So matrix usually follow a trend. What kind of trend? So let's suppose you have a11, a12, a13, b11, b12, b13, okay, b21, b31 over here. Okay, so whenever I write my first, so let's suppose this is 3 cross 3, this is 3 cross 3. So whenever I write, this could be some p matrix, multiplied matrix is p, I mean this, and this p11, this particular p11 is written in certain fashion, right? What is that fashion? I'm going to multiply these things with this particular row with this particular column, right? And this is my first first entry over here. So I can write a11 times b11 plus a12 times b21 plus a13 b31. So notice that notice about these coefficients and the summation sign. So can I write this thing in index notation? Yes, I can write. I can do some summation over here. I can write a I comma k. I can write that times b k comma j, and then I will write p as I comma j. So this would be my index notation for this particular thing. Let me and this goes from k is equal to 1 to 3. Okay, let's see how. So and this pij, this is my ith row and this is my jth column. Okay, and can I drop my summation sign over here? Yes, I can drop. I can equivalently write aik times bkj. Okay, so aik bkj can be written as pij over here. So I want to write what I want to write. I want to write p11. Let's see p11 is what. So p11 is I is equal to 1, j is equal to 1, and I have to write summation over a1k bk1. Okay, and k is equal to 1 to n जाना है, 3 तक जाना है. ओके, सो k इज इक्वल टू 1 रखना है पहले यहाँ पे, तो k इज इक्वल टू 1 पहले रखिए, a11 b11 प्लस k इज इक्वल टू 2 रखना है जोड़ के, सो a12 b21, k इज इक्वल टू 3 रखना है, a13 b31, which is very much similar to what I have written over here. So these are the ways to write your matrix multiplication, because we are not going to write things in details. We just I mean from now onwards I just write this thing and you should know that this thing is this thing. Okay, this is what our perception would be. Alternatively, one more way to write is this: p is nothing but a dot b, or it can also be written as pij is equal to a. I can drop actually k sign over here from here, so a dot b ij. I can also write in this fashion, but this writing in this form or this form would be a better thing to understand that this would be written in terms of this. Okay, so today we'll stop over here. Next day I will also talk about something called contraction, and we'll talk a real force on a surface through index notation. We'll talk about. So yes, any doubts so far? And I agree that I'm going slow, a bit slow, because every class, I mean every other even thermodynamics, I was going slow. But once we achieve a understanding of what we are actually going to do, we'll go fast. Okay. Okay. Any doubt?
No, sir.
Okay. Okay. Thank you. And keep reading this book. This is, please keep reading this book, this Kundu Cohen. I'm following this book. You should go it thoroughly. You will understand what it tells. Okay.
Okay, sir.
Okay. Thank you.